Hello everyone. So today we are going to discuss how to model a MIMO channel. MIMO, as all of you know, is multi-input and multiple output. In the earlier class, we had a little flavor of MIMO channel where we had considered many transmitters in the ceiling and there was one receiver. So now we are going to extend this logic and we want to include, say, NT transmitter and NR receivers. So we will try to model such a channel. So first let us understand what is the use of a MIMO channel in optical wireless communication. So it can give you high data rates because if you see in a room, there are multiple LEDs. And there can be multiple receivers. Suppose there is a user, he has a device which has more receivers, more than one receiver. Then, there are individual channels between one transmitter and one receiver, and those are not very high speed. But if you can have many such individual channels, then you can get advantage of high data rate. So this is one use of MIMO channel. And also we can use as in RF for special diversity. So let us try to understand what I mean by special diversity. So for example, in a, suppose, you get n receivers. I mean, there are n received signals. So this is a Rn. This is detector. This is detector. And when you process it, you get some corresponding vector R1 and you get some corresponding vector Rn. And then this goes to some diversity combiner. And you find out the final received vector and then you can process it to get your data out. So what actually is happening here, you are getting signal from different directions and you can process these signals and get the output. And from there, if you decode data, it is likely that your estimate is going to be accurate. So in the diversity combiner, there can be, different types. One is selective combining. So basically, in this case, you see the signal to noise ratio for each channel. Whichever has the highest signal to noise ratio, you pick up that and that becomes your output. So that is called as selective combining. And the other could be maximal ratio combining, where you make use of all the inputs which you have received. Because in the earlier case of selective combining, you have to, every time, the data is continuous and every time you have to measure which has the highest SNR. So in order to do away with this procedure, one can use maximal ratio combining and then you combine in terms of the weightages. You assign different weightages depending upon channel conditions and things like that. You assign different weightages to different inputs and then try to find out your output, which is called as maximal ratio combining. So it takes care of the weightages in terms of signal channel conditions and whether you are getting low quality signal or high quality signal. The third could be equal gain combining, where you co-phase all the inputs which are coming and then give same amount of gain to everyone, and then try to find out the output signal. So this is another method of getting output signal, equal gain combining. The fourth one is switch combining. So you basically keep on scanning the inputs. Whichever has the threshold higher than some threshold value, then you select that and you continue to work with that signal till it falls below that threshold value. And then you again start rescanning and look for a signal which has more than that threshold value and continue to work with that value, with that threshold, till it drops below that particular threshold value. So this is switch combining. There are various methods. Each method has different advantages. So this is what I mean by spatial diversity. And also it also useful in relaxing, alignment problem. Because for example, in an outdoor system, your TX, suppose there are many TX1, TX2, and this is RX1, RX2, RX2, RX3. Ideally, there has to be a strict line of sight requirement or alignment requirement. You require a strict alignment requirement, but in practice, it doesn't happen that way. There may be a misalignment. The RX might have moved or the TX might have moved. So there is some degree of misalignment between the transmitter and the receiver. So once you have many channels, and then your system can actually learn what is your channel matrix. And even if there is misalignment, and if you know the channel matrix, you can do some sort of electronic processing and try to correct it. Because once you know the channel matrix, those crosstalk element can be found out and you can subtract, and some electronic processing can be done so that your strict requirement of alignment is done away with. So this is another example of having MIMO channel. This is a case of a outdoor system, for example. So you get diversity advantage, you get speed advantage. So that is why we will now explore how VLC or visible light communication inside the door can be used in a MIMO context. Also, let me tell you, before finding out the channel modeling for a MIMO system, angle diversity receiver. So angle diversity receiver, in this case, what happens actually, you have, many receiver at different angles. For example, this is hexagon, so there may be a receiver here, there may be a receiver here, there may be a receiver here, and there may be a receiver here as well, here as well. And this receiver collects light, say for example in this cone, this collects light from this cone. I mean, it is designed so in such a way that there is no area which is left out. I mean, any receiver will get light from, can get light from any direction. So this may get from this. So these are, the receivers which are at different angles. Though it is cumbersome to make such a receiver, but it gives much better performance as compared to a single receiver. So for example, and each receiver, for example, has its own concentrator gain, has own preamplifier which will amplify the signal. So this is a dual receiver, and you can always change this angle of FOV and can make in such a way that there is no area which is left out. So for example, if you make a wide FOV here, and this is also FOV here, so basically light is captured at least by one receiver. So this is how angle diversity receiver looks like, and the advantage is that there will be a direct contact or direct alignment with the transmitter. So wherever the transmitter is, there is some direct contact. So once you have a direct alignment with the transmitter, that is direct alignment with the transmitter, so this will result in high SNR and you can get good performance, right? So, and suppose there is some blockages coming in one particular receiver, the light might come through a different path. It's collected by a different receiver, which is at a different angle. So it is a good solution when you have blockages in the system. Blockages. And since there is a direct alignment, and you may not be getting signals from, say, other sources or from reflection. I mean, you can always make your reflectivity in such a way that your reflection coefficient is designed in such a way that not enough non-line of sight component is falling onto the receiver. There is only a LOS component falling. So once you ensure that, which can be ensured using angular diversity receiver, then there will not be any intersymbol interference. Your data rate will be high. So these are some of the advantages of, angular diversity receiver. So this is a case of actually a MIMO. I mean, you can have many transmitters, and here, there are multiple receivers, and you get, these advantages using angular diversity receiver. So now we will study or try to find out the channel for a MIMO system. So there are two types of MIMO system, optical MIMO system. One is non-imaging, and the second one is imaging optical MIMO system. So first let us start with non-imaging. So non-imaging system non-imaging system, suppose let me make a room here. So you have transmitters or the LEDs installed here. It can have some specific geometry of putting the transmitters on the ceiling, and on the receiver, your receiver actually, for example, has for example 4 RX, or there are 4 receivers. So the light, and each is independent. It has its own concentrator and has its own preamplifier. So the light will fall onto these receivers. So this is a case of non-imaging. Non-imaging optical MIMO system. Now let us try to find out the H. So this is going to be a matrix, because let us try to understand this in this fashion. You have suppose this is your transmitter. There are 4 transmitters, for example, say here, and this is receiver here, this is receiver here, this is receiver here. So this receiver can have light from here, can have light from here, can have light from here, can have light from here. Similarly, this receiver can have light from here, from here, from here, from here, and so on and so forth. So this actually is a matrix, which is called as channel matrix, MIMO channel matrix. So in this case, it is going to be a 4x4 matrix. And each will have component Hij, where I is equal to 1 to 4 and j is equal to 1 to 4. So we'll try to model this H, which is a matrix. This is what we want to do. So let me draw a system here. Maybe let me draw in the previous page if possible. Let me draw in this page itself before we go to the more description. So typical optical system will be optical MIMO system should look like this. Suppose this is your input and it has input says 0, 0, 0, 1, 1, 0, 1, 1. So first we will use serial to parallel. And I will get 4 outputs for this stream. So this will be 0, 0, this will be 0, 1, this will be 1, 0, this will be 1, 1. And this stream is given to a LED, which has impulse response. Say this is LED 1, which has a response HLED. Similarly, this goes to this LED, this LED. So each has a LED and response HLED-T. And this output, which is now optical output, you can have some sort of, optics here. And on the other side, you have the receiver. So this is some optics here, concentrator gain or whatever you want to have. And this is your photodiode. This is photodiode 1, this is photodiode 2, so on and so forth. This is PD3, this is PD4. Now, as I mentioned, the light from this LED can fall onto all the systems, all the receivers. Similarly, for this, so I'm not drawing for the third and the fourth one. It will complicate here. And then each PD, there is some, when you model, there will be some noise added. Could be natural noise, light or some artificial light, and the noise generated by the photodiode itself. So this is the noise part. And then they may have some preamplifier. So basically you will get 4 such outputs. So noise is getting everywhere. And this is PA for each branch. And then once you have this, then you can have H inverse, whatever the matrix you have H. If you have the H inverse, then you will be able to get the output. So this output will come here, and then some low pass filtering, some processing at the receiver. This is low pass filtering, and then you get back your outputs, and then it is parallel to serial, and what you get is a estimated or recovered output, the RX. So for recovery, I need to know this channel matrix so that as a receiver, I can find out H inverse and do the processing and recover my data. So it is very important to understand how to model the channel matrix. So the question in front of us is how to find out this channel matrix. So let us assume that this is a transmit vector, T1, T2 to T and T. I'm assuming NTTX. So this is the transmit vector, capital T. TI actually here is, the TI is that input data stream convolved with the impulse response of the LED. So this is what this TI is. And I am also assuming that the source is a Lambertian source, and it gives the average power of PLED. So if I'm using on-off keying, that is in the on, there is no output, and in the off, in the off, there is no output. In the off, there is some output. And if the average value is PLED, that means the range of low and high is between 0 and 2 LED, 2 power LED. So that will be the maximum power corresponding to 1. And the average power is 1. So this average power is PLED, and it's a Lambertian source. And I'm assuming NT transmitters. There are NT transmitters on the ceiling and NT receivers. So I'm trying to find out the channel gain, DC channel gain between TXI and RXJ. And this DC channel gain, as I had earlier explained, the bandwidth of the channel is quite high as compared to the bandwidth of the devices, the LEDs and the receivers. So it is actually a flat channel. So I need to just calculate only the DC channel gain between a transmitter I and transmitter J. And also I will assume that I'm not having contribution from non-line of sight. I mean, this is a valid assumption to make, because if you see, there is a strong component which is coming from line of sight. So as compared to non-line of sight, it is much higher and can be neglected. Although when you're doing some rigorous analysis, you'll have to consider the non-line of sight component. But just to understand about the channel modeling of a MIMO, let us for the time being ignore that there is no significant contribution coming from non-line of sight, because it can be seen that the non-line of sight component is actually 10 dB lower than the weakest line of sight receiver getting the signal from any of the LEDs. So if it is in the direct contact with any transmitter, that difference is even higher. But even with the weakest line of sight, which is coming from some other transmitter, the line of sight component contribution is at least 10 dB smaller than the weakest line of sight link. So for practical purposes, we can ignore non-line of sight, and we are assuming here DC channel gain, assuming the gain of the channel is higher, which we had discussed earlier, that it is about 100 megahertz, where the devices are maximum 20 megahertz. So the channel is actually flat. So from our previous understanding, Hij between ith transmitter and jth receiver is given by this. Now let us understand what is this capital K. So in the system, what I have assumed that, there are, for example, 4 transmitters. Now, each transmitter has LEDs. So it's an array. Each transmitter is an array, and this array has LEDs. Could be 60 cross 60 or 20, depending on what illumination level you want. So this value can be different, cross 60, or it could be even smaller value. So this K is actually number of LEDs in a panel. So this is a panel which has these number of LEDs. So this capital K actually depends number of LEDs in that panel. And AJRX is the receiver collection area for the jth receiver. And D square IJK actually is the distance between ith transmitter. This is, let me write here, ith transmitter and jth receiver for the kth LED. As I told you, there are many LEDs, 60 cross 60. So this is for the kth LED. So that is why you see the sum over all LEDs here. I05GK, you can again find out that angle, emission angle, which is between transmitter I and transmitter J for the kth LED. And this is cos psi jk. This is how we had modeled earlier. And these are the conditions. It will give some value when, as long as it is between 0 and that FOV. This is FOV. And this will give you 0 when it is greater than FOV. Psi C is the FOV. And again here I have not included optical filter gain and concentrator gain, assuming they are all 1. So it does not change actually the theory. So I'm assuming those to be 1. So the channel matrix H for such a system can be written as H11. These are all components here. So this is, for example, receiver here. So this is going here, this is going here, this is going here, this is going here. So this is H11, for example. This will be H12. So on and so forth. So you get a matrix, which is NR cross NT matrix. So this is the channel matrix.